All right, hello and welcome back. So we're going to continue with this idea of waves, but now we're going to talk about their application, namely how we can harness waves for technological purposes. So before we actually talked a little bit about that with noise canceling speakers, or headphones, I should say. The idea that you can mix in an opposite sound from the backgrounds around you, and it will cancel out that background sound, and then you just get to listen to your music. No annoying refrigerator humming in the background or coffee shop noises or things along those lines. Well, this time we're going to talk a little bit more about communications, but still the same idea that we're using properties of waves to communicate in some way or to harness it for the purposes of a technology. So to get started, we'll talk about the basics. Remember, per usual, you need 3 or more bullet points worth of notes, a 1 to 2 sentence summary. So to get started on this lecture, what is the difference between amplitude and displacement? So think about it, looking at this image. Is the displacement changing in this image? Is the amplitude changing in this image? All right, so hopefully you thought about it for a second. In this case, we can take a look at this and see that the y-axis is literally showing you displacement. The x-axis is showing you the displacement at different times. So for a single particle, what's happening is at time of 0, it's here in the middle, but at a time of 0.5, it's already displaced up to 5. But by the time it's at 0.1 seconds, it's back down in the middle, and at 0.15 seconds, it's down at -5. So over time, it's just kind of vibrating back and forth, and that's what we're seeing with this graph. So we can see that the displacement is constantly changing. It goes from 0 to 5 to 0 to 0.5, and that is because it's vibrating or because it's a wave. Now, amplitude is not changing. The amplitude is the maximum displacement, and so we can see that the maximum displacement stays the same in this case. It doesn't always, but this case it does. So it's an important distinction because we're going to be talking more about this idea or using this idea of displacement right now. So thinking back again, what happens when you overlap two waves? Like pretend we have this S wave and this C wave. What happens when they overlap in the same place at the same time? All right, so hopefully you said they combined, and they do. And so we can see that that combination is really an adding of the two displacements, where this one right here is twice as big as this one at the very beginning, and so it adds to, you think about 2 plus 1, so it's like a height of 3 right here. But here later on, this one is 0 and this one's a -1, and we can see it still kind of adds that -1 in. So it's the displacements that are adding, not the amplitudes that are adding. Right, so we had this S wave and this C wave. Now imagine with this combo wave that we took it and instead of adding another C wave, we added the opposite of the C wave, so a negative version of it, where the original C wave goes up, this one goes down, and vice versa. So what if we added this negative to version of it to our combined wave? What do you think would happen? What would it look like? Take a second, think about it. Alright, so hopefully you realize we're actually subtracting back out the C wave, so the carrier wave is what we'll call it. So here where we added it into the signal wave, here we're subtracting it back out, and the result is our original signal wave. It'd be like if you had $5 and I gave you $2 but then took $2 back from you. You just get back to your original $5 amount. So here, that's what's happening. We get our original S wave back. Now, for the purposes of the rest of this lecture, let's call that S wave the signal wave. And the signal wave would be, for example, your music or your voice if you're talking on a cell phone, or it's the little bits that are being sent to communicate your text message or whatever it is, your TikTok, etc. So here we've got this idea that the S wave is the signal wave, and the C wave is the carrier wave. If you think about radio technology, it's the station you're tuning into. It's the thing that carries the signal along. So we'll talk more about that in a second. All right, so we think about communicating, and usually most of our communications, although maybe not as much nowadays, but start often as a voice or as a sound of some sort. Not always, again, but many times it does. And so sound is a wave, and often when we see it on a computer screen, it looks something like this, where you see a lot of kind of spikes and jagged, but it doesn't really look very wave-like. And that's because the frequency of our communications is so high that all the waveforms are scrunched together over a very short period of time, and so we can't really separate them out. But what we can see is kind of the peaks in volume here. So I'll play this gull sound for you in a second, and you'll be able to hear that as it kind of caws or makes its noise, as it spikes, that's the spike right here. So I'll play it. Cool, so hopefully you were able to hear that sound. And so again, here we're able to hear somebody say this is a recording, and so kind of in those pauses between each word, we can see that the volume goes down, volume being kind of the amplitude or maximum displacement at any given moment. And so that's what's going on there. Cool, so hopefully you heard that. So we've got this idea that this is what waveforms look like, even though it doesn't look very wave-like. If we were actually able to zoom in, for example, on that voice speaking, what we would see is something that looks a lot more like a wave that we're used to. It's just that our voices are often in the like 1,000 hertz range and things along those lines. So we're literally getting 1,000 vibrations each second. So that's why they're super, super smushed together and hard to tell apart unless we're zooming in on a tiny portion. All right, so communications, sound, whether it's voice speaking or music, are all in waveform like this. And so what we're going to talk about is how do we actually send that music or that singing or whatever it is through the radio, and that's what we're going to focus on. So to send a message, we start with a microphone, which translates our actual sound of us speaking into an electronic signal. So it captures it in this waveform electronically. Now, somehow we have to figure out how to send that waveform across the airwaves, and so that's what we're going to walk through right now. So the process for that is we combine the electronic form of our signal with a carrier wave. So you think about a radio station, it has like a tuning frequency that you go into, whether it's 106.1 or 106.7 or 98.9 or 94.9. Some of those are local, some of those are not. But we get the idea that you can add on your signal to the set frequency or carrier frequency from the radio station, and then later on you can actually subtract it back out. So on the receiving end, what happens is the radio receiver hears that combined wave and then subtracts out the carrier wave and then just plays out your music. Now, it's a lot more technological than that, but that's the basic process of it. All right, so to review real fast, the first step is you capture your sound wave, or whatever medium it is, you need to capture it and turn it into an electronic signal. Step 2 is you combine your electronic signal with a carrier wave, and then you're going to send that out via, in this case, radio waves, so electromagnetic waves that are going through time and space and are able to, travel across the area. And then lastly, when the radio wave is received on the receiving end, you usually have an agreed upon whatever the carrier signal is, you subtract it back out, and you're left with your original signal wave. And then you can translate that into music or a picture or whatever it is that it was originally. So that is the general process for how communication works. Again, that's a very general process. We're not getting into the specifics. All right, so now that we've covered the basics of how kind of radio signals are sent, let's think about some specifics, like what is the difference between AM and FM? What do they stand for? Now, one thing you can notice with FM and AM right now is that one of these is in megahertz and one of them is in kilohertz, so we can see that FM is at much higher frequencies. But let's talk about what AM and FM stand for. So AM stands for amplitude modulation. Now, modulation is a fancy word for change, or to manipulate is another way to think about it. So here, what's going on is we have our radio signal. So think of this as the radio station's tuning frequency, 94.9 or whatever it is. And our audio signal is being mapped onto it by changing that radio signal's amplitude. So it's the amplitude of this carrier wave that is being modified or changed or modulated in some way, shape, or form. Whereas the amplitude goes up here, the amplitude or the displacement of our signal wave goes up, and as the amplitude goes down, the displacement of our signal wave goes down. So that is what AM stands for. So think about it for a second. If we look at a similar signal wave and an AM wave, think about what do you think FM stands for? All right, so hopefully you started to think, oh, F, frequency. That's kind of what's going on. And the M is, again, just modulation. So here we've got this idea that FM stands for frequency modulation. So instead of the amplitude of our carrier wave going up as the signal displacement goes up, we see that the frequency increases. And as the signal wave goes down, we can see the frequency decreases, or the waves spread back out again. So here we've got a radio wave that is being kind of increased in frequency and then decreased in frequency ever so slightly, and that subtle shift and change communicates what the music is, or what the voice sounds like, or things along those lines. So just like before, what radios will do is they will take the carrier wave and they will subtract it back out of the FM wave, or the FM wave or the AM wave, and then they'll, using the radio, pump that into a speaker and play out the signal. Now, neither of them is as simple as just adding and subtracting. It's a little bit more complicated than just a simple add and subtract, but it's the same basic idea, this idea that we are kind of removing that carrier wave. That's it for this one. Remember to do 3 or more bullet points worth of notes and a 1 to 2 sentence summary, please. Alright, so we're going to continue on with talking about the difference between analog and digital. As always, you need 3 or more bullet points worth of notes and a 1 to 2 sentence summary. Alright, so there are 2 ways to send signals, or to record them even sometimes. One is analog and the other is digital. Let's start by talking about analog. Analog means it's continuous. It mimics the real world signal. So if this is our original sound wave, like the actual person talking, when we record it as like an electronic form, voltage varying up and down or whatever it is, then we're going to mimic every single little point along the way. So as this goes up, and we're going to try and record every single bump and dip and little bit that's there. And that's what analog does. So if this were, instead of being voltage varying up and down, if it were on a vinyl record, it could be that the bump or groove is varying ever so slightly on the vinyl record. And so that's what's going on with an analog signal. Digital, on the other hand, instead of trying to record each and every little bump along the way, just says it's going to record at set interval times, or sample is what we call it, at set interval times. So what's going on is, as our analog signal is happening, it is only going to sample once every, let's say, 0.1 seconds, where it says, oh, at this moment in time, it's right here at this value. And then another 0.1 seconds later, it's at this value, but it missed all of the stuff that was happening in between. So that sampling gives the general waveform of what's happening, but it doesn't exactly capture every single nitty-gritty detail. Another example of this would be like if you were walking through life with your eyes open the entire time. That would be like analog. You're seeing everything happen in front of you. Instead, if you wanted something more digitized or discrete in that sense, you might instead close your eyes, and then once a second you would open your eyes for a split second and then close them again. So you can think about how that would work, where, you could probably walk around and still do most of your things, but you're going to miss some of that information, or some of that visual information that happens in between you opening in between the times where you open your eyes. So that's what's going on with digitizing, is you are missing a little bit of the detail of the information, but the benefit of it, so you might be like, why would we be doing that then? The benefit is that you get to send less information. So you think about, if you were trying to send what you saw to somebody and your eyes were open the entire time, you would have to send them a whole set or a whole video where it's showing like every single moment. But if you were to go back to that idea of closing your eyes and then opening, closing and then opening, if you were doing that instead, you would be sending just 5 snapshots or 10 snapshots or whatever it is. So you could be sending pictures instead of a whole video. Same thing's happening with audio or any other digital signal. We're sending samples or discrete just pictures or snapshots in moments of time of where that signal is, and then we use that to recreate what's going on. So we can see that this form down here being discrete can kind of recreate what was going on here, but we do lose a little bit of the detail. And so this is why if you listen to MP3 music or other things, as you increase the file size, they're taking more and more snapshots. So once every 0.1 seconds instead of every second. And that adds in more detail, but it also is more information. So oftentimes though, if we think about kind of signals here, so far we've been looking at this as kind of literally trying to mimic its height of the original signal up here. Oftentimes instead of doing that, kind of hinted at it over here, we use codes instead. So instead of trying to record literal ups and downs, what we do is we translate that into just a code that says, oh, this value is at 5, this value is at 6, this value is at 4. Well, I guess that would be 5.5 or so. And you can limit the number of values that you have. And so that's kind of like if you imagine Morse code. So back when they had telegrams, what they would do is they would send a little electronic beep, and they didn't have much room to work with, so they couldn't like send their voice. They were just literally sending a little beep. And so to communicate, they developed a code where they had a set of long beeps and then short beeps, or dots and dashes as are often called. And they could use those dots and dashes in different combinations to send the message. Now obviously they're sending a more limited message, but that's the idea. Similarly, computers and most digital communications send a message in binary code. So you can think of us as either silence or a beep. So there's no dash here. This would actually be trinary for Morse code, and this is binary, or only 2 values for binary code. Now, oftentimes we'll use 0 and 1 on binary code as representative, but it could really be a high voltage and a low voltage, or an on and an off, or things along those lines. Now, you think about it, okay, we've so far started this idea of, okay, we have analog and it's continuous and it's a lot of information, and with digital you can reduce the amount of information. And then we talked about this idea that you can use codes, because if you are only communicating certain values, you can just code it as a certain thing, the code for 4 or 2 or whatever. The question is, why would we use that binary code? What benefit does it have? Well, it actually has a pretty significant benefit in terms of getting rid of static and things along those lines. So if every value in our digital signal is either a 0 or a 1, or a low or a high, whatever it is, then we know exactly what we're looking at every single time, because it's very rare that anything would be in the middle here, or etc. So it's either going to be up or it's going to be down. With an analog signal, you're actually tracking every single individual movement, and so you can't decode that as well. It has all that information to decode, but if there is a little bit of error in there, we don't know how to separate out that error. So here, if we're looking at this recorded signal as the static or tape hiss in this case is added onto the original signal, we don't know what part is static and what part is the original signal. We can't separate it out. But if we're looking at this digital signal, we can see that as the static or tape hiss is added to our signal, we still get a general sense of like, oh, this is all 0 down here, this is all 1 up here, or low and high, or things along those lines. And so you can subtract out that interference. So the real benefit of using a digitized signal, whether it's binary or something else but digital, is that A, you can reduce the amount of information you're sending, so you can compress it and store more information, or more time of information, even if it's less quality. And then B, it's easier to clean up the data. So you can subtract out any interference or other things, because you are able to know that everything's just going to be 0, 1. So if it's at 0.95, you can be like, oh, that's just a 1 kind of thing. So you get to round. So that is the main benefit. Another example of just binary, just to help you kind of get a sense of it. So looking at this, we see that this would be for like voltage for a transmitted signal. So this would be the 1 value, this would be the 0 value, even though none of them are technically at 0 already. But we just use that as the signal. So it just kind of bounces back and forth between 0 and 1. That's it for this one. 3 or more bullet points worth of notes, 1 to 2 sentence summary, please.